All right, welcome back. So we have introduced this linear differential equation with forcing. In fact, this is a system of linear differential equations with forcing because A is a matrix and B is a matrix and X is a vector containing all of the states of my system. And this is a really, really important equation in applied math because this is how we model systems that we might want to control or that are externally forced. So very, very important to be able to solve this. And today I'm actually going to derive this full-blown solution here in terms of this convolution integral and this e to the at x naught. And I'm going to build it up very, very simply in little kind of bits and pieces. I'm going to introduce the Dirac delta function and kind of build up this convolution integral here from scratch. This is going to be a pretty important, interesting lecture, and it's actually going to involve a little bit of math. So this might be a little bit more on the challenging side, but I hope to make it extremely intuitive, so anytime you see this kind of system, you know exactly what all of these terms mean, you know how to derive it, and you know how to work with it. All right, let's get started. So the first thing we're going to do, and in general, this is how we handle differential equations with forcing usually, is we're going to start by just looking at the unforced or homogeneous equation, x naught equals ax, with some initial condition x naught. Okay, so kind of the first thing we're going to do, and I'll have to be a little careful with my color management here, the first thing I'm going to do is kind of case one is going to involve no control, so u of t equals 0, and an initial condition, some initial condition x naught. Okay? This is kind of the trivial case. I'm going to start really, really simple. What is the solution in this case where there is no control? Obviously, we know the answer to that. We know that the solution, this is the same as x dot equals ax with no bu, because u is 0. And so the solution is x of t equals e to the a matrix times my initial condition x naught. Okay, this is the solution for the unforced system. And what I'm going to show is that you can essentially solve different subproblems of this big forced problem and then add them up to get this, this full expression here. Okay, so this is kind of the simplest case with no forcing, kind of the homogeneous solution. This is often called the initial condition response. That's what I'm going to call it. This is the initial condition response. Okay, and that makes sense. It's literally if I have some initial condition, this is the response of the system to that initial condition. And what I'm going to show now over the next 5, 10, 15 minutes is that for a generic control input u, I'm going to draw maybe a little picture at some point. What I'm going to draw is that for some generic control input u, for some u of t, let's say this is u of t, what we're going to do is we're going to think of this u of t as a sequence of little kind of teeny tiny little impulses, these little delta u's, these little, literally like in calculus and Riemann integrals, we're going to think of these as a bunch of little delta u's. And what does a delta u do to my system? So that's what I'm going to look at case 2, is case 2 is literally going to be, what if I have no initial condition, so x naught equals 0. So these are kind of the two opposite cases. Here I had no control forcing, but I had an initial condition. Here I'm going to have 0 initial conditions, but I'm going to have a control forcing. And I'm going to say, and u of t equals a little delta function. I'll define what I mean by a delta function, but it's literally kind of like one of these little, a little discrete delta input to my system. I'm going to kick it a little bit. It's a kick to the system. And I'm going to say my B matrix, let's for now say B is actually in the direction of this x naught vector. Okay, so B, this B matrix is just a single column, which is the column given by my, my x naught from up here in case 1. So this x naught was a vector of initial conditions, and I'm going to pretend that this B matrix is that vector of initial conditions. Okay, so bear with me. This will make sense in a minute. Okay, and what I'm going to do is I'm going to show you how this works. Okay, So in this case 2, this is going to be called an impulse response, because I'm giving an impulsive input to my system U. So many of you might be thinking to yourself, what is the symbol delta t? What is this delta function, this like discrete delta input that Steve is talking about? So right now I'm going to give you a little 5 or 10-minute vignette on what is the impulse response, what is this, this Dirac delta function here. So delta of t is known as the Dirac delta function, a Dirac delta function. And it's like a generalized function. It's a weird function because it has some strange properties. It's actually not like a well-defined function. It goes to infinity at t equals 0, but it has an infinitesimal width so that its integral equals 1. So it's literally defined so that the integral from minus infinity to infinity of delta of t dt equals 1. So it's a shape that is infinitesimally skinny and tall and has area 1. So if you like, you can think of it as the limit of a little rectangle. So let's say this is t, and let's say that this is 0. And what you can do is you can take a unit width rectangle. So it has height, let's say it starts with height 1 and width 1. And I can start taking the limit as this becomes skinnier and taller so that it still has area 1. So I could take it twice as tall and half as skinny, or I can take it 4 times as tall and a quarter as skinny. And I take the limit kind of as this thing becomes infinitesimally wide and infinitely tall, but so that its area is still equal to 1. That's what this delta function is. That's the Dirac delta function. So if I integrate it, its area equals 1, but it is infinitely thin and infinitely tall. And you can do that with rectangles. You can equally well define your delta function as Gaussians. This is my 0 line, where I take the Gaussian so that its area equals 1, and I take the limit as the variance becomes infinitesimally small, kind of infinitely small of that Gaussian, and eventually it becomes a smooth, very peaky delta function. Okay, so again, this kind of progression as you take this variance to 0, this Gaussian, this unit area Gaussian will approach this delta function. That's how this delta function is derived. And in fact, you don't even have to take the integral from negative infinity to infinity. The integral from minus epsilon to epsilon of delta dt equals 1 for any positive epsilon. Even if epsilon is 0.000001, the integral from minus 0.00001 to 0.00001 of my delta function will equal 1, because this thing has unit area and it's infinitesimally small. So it's entirely encompassed between minus epsilon and epsilon. Right, so all of its area is between minus epsilon and epsilon for any epsilon you can name, even if it's teeny tiny. Okay, so this is a weird construct. Why am I inventing this crazy function that has these properties? It turns out Dirac found this very useful in quantum mechanics. This is a necessary function to do the kinds of calculations that we need to do that I'm about to show you. And so the delta function has this interesting property. So sometimes what I'm going to do is I'm going to draw my delta function as, let's say in time. Often I will draw my delta function as an up arrow. That literally is the symbol I use to mean this kind of limited delta function that has unit area, but it's infinitely skinny and tall. And let's say that this is u of t equals, some delta of t. And so this is t equals 0. Then the integral of u of t is going to be 0 for all time less than 0. And immediately when I cross over 0, my area is going to jump to 1. Because this has, and I think it jumps to 1 like that. Because again, this delta function has unit area. So if I integrate past the t, where that delta function is defined, my area instantly jumps to 1 and stays there forever. So that's how this function works. It's a weird function, but it's very, very interesting and useful. And we're going to use it here. We're going to assume, and mathematically, the way I think about this in control systems is, I think of this as an impulse to my system. So if I have my mass on a spring, and I whack it with a hammer, I just like bang as fast as I can, so it's super, super short in time and a lot of energy. There is a finite amount of energy I'm putting into that system, a finite amount of area or energy I'm putting into that system, but I'm doing it in an extremely short amount of time. So that whack, that impulse, mathematically behaves a lot like a delta function. And so that's why it's super useful in control theory. That's called the impulse response. Often, if you have a system, you would literally like whack it, with a little impulse of energy, watch how the system responds, and that would be a useful way to characterize your system. Okay, and that would technically, physically, that would correspond to, maybe a rectangle with a very, very small width and a very, very tall height. Mathematically, we're going to approximate that as a delta function because it's going to be better behaved. One more property I want to show you about the delta function. I'll show you this property in a minute. That's delta functions. So let's come back here. So we know how to solve this system if u of t is 0. How do we solve the system now if I have no initial condition, but I have an impulsive input to u? And I'll just write this down that like x dot equals ax plus bu. That kind of implies that x of t equals the integral from wherever my initial condition was. Let's say whatever my initial t naught to t of everything in here. I would just integrate, ax plus bu. These are all functions of tau d tau. Okay, x is a function of tau, u is a function of tau, integral d tau. And if I start with 0 initial condition, so I'm actually going to draw this response here of x. So this is, x of t. Let's say this is t, whatever my 0 time is. And I'm also going to show my u of t. And remember, at u of t equals 0, I get this delta function. So I have a delta function right here at t equals 0. And so if I think that my x of t equals the integral of all of these dynamics, right, because literally I integrate in time and it's the integral of this, and so on and so forth. If I start with 0 initial conditions, I start at 0, 0, 0, 0, 0, 0. It stays 0 for all time. This is 0, 0, 0. For any negative time, this is 0. And then immediately at t equals 0, this u is a delta function, so the integral right past that point jumps up to 1. So this jumps up to 1 at time 0. Well, it technically jumps up to whatever b is. It jumps up to my value of b, which is x naught. Let's say x naught. And then for all future times, this u of t is equal to 0 again. But now it looks like I have an initial condition because my x jumped up to whatever b times delta, if I integrate that, it integrates up to b times 1, which is b. And I claim that I made b to be this initial condition. So what I'm getting at is that this looks a lot like an initial condition response after the delta. So before the delta, it's 0 dynamics, so x equals 0. Exactly when that impulsive delta happens, what's happening is that the integral immediately jumps to 1. This integral of u immediately jumps to 1. And so this x immediately jumps to whatever this b vector is. So x at time, I would literally say x at time 0 plus, an epsilon, an instant past times 0, x naught equals whatever b is. And I've chosen that to equal x naught. So I'm trying to convince you that this impulse response looks like an initial condition in this b direction. So now I have an initial condition in that b direction. And even though u is 0 for all future time, now x is non-zero, and so now the system evolves as if it was x dot equals ax with this initial condition. And let's assume my dynamics are stable, And so now this is what my future time response is. This is literally going to be e to the at times that x naught. And I didn't have to set b equal to x naught. I could have had some arbitrary b, and then the system would jump to x naught plus equals b. This would equal a b, and this would be a response e to the at times b. Okay, maybe that would be an easier way to think about it. So the long way of saying, because I've defined this fancy, funky delta function that has unit area but infinitesimally short. It's like if I hit my system with a hammer and just immediately at time 0 inject some energy into the system, some finite energy into the system. That's what happens here. If I have u of t equals a delta, I inject some finite amount of energy into my system. It looks like starting at an initial condition x naught equals b. So at that time, t, it looks like my system started at that initial condition, b. Okay, good. One more thing I'll show you is, let me see, so an example of this, so kind of an example would be, okay, let's try this again. Let's say we have x dot equals ax plus bu, and I have x naught equals 0. And I have u, now I'm going to say u equals delta t minus 5. Okay, we're going to look at what delta t minus 5 is. Okay, so instead of a delta at t0, I'm going to have a delta when t equals 5, so all the way over here. Okay, so we're going to look at what that looks like. So this is u, this is t. Again, let's say 0 and 5. This is where my delta function happens. I probably shouldn't draw arrows here on my left axis, even though I usually do. Okay, this is my u-axis. My u-axis. And I have a delta function now at t equals 5. You can convince yourself that when t equals 5, this thing has a delta. The delta function is infinite at 0. And so this thing occurs when t equals 5. That's when this delta function impulses to the system. So that's what u equals. And so what is our output response x? Okay, this is t, and this is x, and this is 0, and this is time 5. So again, just like we saw here, my initial condition is 0. So kind of for all time before 5, u is 0 and u is 0 and x is 0. So let's say x is 0. So for all time before 5, x is equal to 0 and u is equal to 0. So x of t equals the integral of 0 is 0. But now at time 5, the integral of ax plus bu, immediately we gain some impulse in energy because this is a delta function that has area 1. So immediately at time 5, my system jumps up. It jumps up at time 5 to being a value, which essentially that value would be x at time 5 plus epsilon equals the integral of b times that delta function is b. So, you know, x and b. X equals b exactly at time 5. So, you know, this is whatever b is. And I'm drawing this as a scalar, a single x. But, you know, if x has 2 components, then this would be, you know, the first component. There would be another plot like this for the second component. And the first component of x would equal the first component of b. And the second component of x would equal the second component of b. X is a vector, b is a vector. And immediately at time 5, x kind of jumps up to a value equal to b because of this impulse in u. So, you know, x, if I integrate this thing, then immediately when this thing gives me an impulse in energy and integrates to 1, then x at that time equals this b vector. Okay? And then for all future times, u goes back to 0, but now we have this initial condition at x equals b. It's kind of like an initial condition. And so then the system dynamics take over, and this is e to the a. Now it's t minus 5, because all of these dynamics start at t minus 5. Times that initial condition b. Okay, so this is literally what the trajectory would look like for all future time. So for you can literally say x of t equals 0 for t less than 5, And for t greater than or equal to 5, it equals e to the a t minus 5 b. That's the solution of my system. Okay? Fantastic. Okay, so we now have the building blocks to now start to think about this general system here, okay? And I claim that now I can combine these two. I can take a system that has a non-zero initial condition and a delta function at some time, and I can add those together, and I will get the superposition of those two. So I'm going to draw that as the last example before I tackle this general case. I'm going to erase this part of the board, so just stay put. Okay, I'm going to do one more example of delta functions before I tackle this general case. And again, remember, in the general case for an arbitrary control input, that does some function u of t, I'm going to break that down into a sequence of impulses. So I want to make you feel comfortable with these impulses. Okay, so case 3. We're going to combine an initial condition response and this impulse response. I should probably say this here is called an impulse response. An impulse response. It's literally the response of my system if I gave it a delta function input. And when I say delta function, you should think I hit my system with a hammer really fast. I give a finite amount of energy in an infinitesimally short amount of time. That's what an impulse response is. Mathematically, we write it as this delta function. This is an impulse response. So here I'm going to combine an initial condition response and an impulse response and show you what happens. So here now we're going to say u of t equals a delta function at t minus 5. So we're going to keep our delta function at t minus 5, this impulse at time 5, where b is, it equals b. It's not, I'm not going to make it x naught. This was a little confusing. It's just going to be some vector b that I choose. B is b. And we have, x at time 0 equals x naught. Okay? That's now the system that we're going to solve, and I'm going to plot everything as if b is a scalar number and x naught is a scalar number, but this works for vectors x and vectors b. Just do what I'm doing for every single component, x1, x2, x3, x4. Okay, not too bad. And so what I'm going to do is I'm literally going to take the sum of this impulse response and this impulse response and this initial condition response, and that's going to be my solution. So let's just do this. And I'm going to try to give myself enough room here. So this is time. And let's start with my, my initial condition response. My initial condition response is going to be that at time 0, my system x is going to be, it's going to go from 0 to x naught. This is x naught. So it's going to go from 0, and at time 0, it's going to be x naught. And then the initial condition response is just e to the at times x naught. And I'm going to draw this for a stable A matrix where it has negative real eigenvalues, just because it's going to look easier. So, sorry, it's so squeaky. This is e to the at x naught. Okay, that's my initial condition response. And I claim that the full solution for this initial condition response and this impulse response is just the sum of these. So it's plus my impulse response, which again, what we're going to draw is x versus t, time 0. Let's say this is time 5. And at time 5, that's where we're going to have our delta input at time 5. And so at time 5, our system, let's assume we had a system without an initial condition. So we're solving the initial condition system with 0 forcing. Now I'm going to solve the system with 0 initial condition, but with this forcing. And so for that system, it is 0, remember, until time 5. And at time 5, I jump up to a value b. And then my response afterwards is e to the a t minus 5 times b. And it's t minus 5 because my decay starts at time 5. Whatever my dynamics e to the at are, they start at time 5, starting based at time 5. So it's t minus 5 here. And so I claim that my full system response, my actual, and this is my impulse response, So I claim that the total system dynamics here are now given by the sum of these two responses, which is kind of nice and easy. So I have times 0. And this is because linear superposition holds, because A is a matrix, not a nonlinear function, and B is a matrix, so linear superposition holds. And I'll tell you more about what this means, but essentially it means that if I start at, if I give it one control input u and another control input, and then I add those two control inputs, the output will be the sum of the two independent outputs. So if I have control input 1 and control input 2, and I have response 1 and response 2, then if I sum those control inputs, the response is the sum of those two responses. That's what it means to be a linear system. I'll have a whole lecture talking about that. Maybe I've already posted that. And so here it means that I can sum up my initial condition response and my impulse, and I get something that now looks like this. So it's going to jump to x naught here, and it's going to be decaying, but it's not going to be completely at 0 by 5, and then it's going to jump up to, this is going to be b plus whatever, e to the minus e to the at. I'll write this in a minute. And then it's going to, again, slowly decay. So for here, this is, e to the a t x naught. Here, this is e to the a t minus 5 b plus whatever e to the at was, plus e to the a t x naught. And starting at t equals 5, there was still some non-zero remainder here. This wasn't all the way decayed to 0 yet, which is why I drew this a little bit larger than 0. This little delta here, this is e to the a 5 x naught. This is e to the a 5 times x naught, where t is evaluated at 5. And so this is the full solution here is, for times less than 0, it's 0. For times between 0 and 5, it's e to the at x naught. And for times greater than 5, it's e to the at x naught plus this impulse response, e to the at minus 5 times b. So I hope this makes sense, that you can break down your solution into an initial condition response and the effective control. And I've been keeping my control simple, these like very discrete punctate impulse responses, because those are the easiest ones to solve and to integrate. When I have an impulse in u, then for all times before that impulse, nothing happens. And then immediately after the impulse, it's like I had an initial condition at x equals b. And we know how to solve these initial conditional responses. So I'm trying to convince you that my impulse response looks a lot like a new jump initial condition. It's going to jump my initial condition, and then my dynamics take on after that. So now, armed with this, I'm ready to show you how to do this for a generic u of t and how to derive this function. So I'm going to erase some stuff, and I'm going to draw some stuff. Just stay put. OK, I realized I might need the entire board for this one. So what we're going to do is now solve for that output response where my input u of t, this is t, where u of t can now be an arbitrary function, not just an impulse. And what I'm going to do is I'm going to break this down into a bunch of little teeny tiny impulses. So I'm going to, I'm going to basically say I have, time 0, time 1, time 2, time 3, ... all these kind of little times separated by delta t. Okay, so tk plus 1 minus tk is delta t. These are little like fixed delta t time steps. And I'm going to approximate the area under this curve as a little delta function with that area. And so my Riemann sum, so I'm literally going to say that I'm going to draw the same picture over here because I'm going to use this one to draw like the summation. And here I'm going to draw kind of what I mean by this delta function. So what I'm going to do is I'm going to approximate the area in each of these little bunches, each of these little Riemann area pieces, each of these little rectangles. What I'm going to do is I'm going to approximate that as a train of impulses, as a little train of impulses. So this is an impulse, this is going to be a slightly bigger impulse. I mean, you can see kind of that this should match the shape of U because these impulses are related to the area under each of these curves. And so this impulse is going to be, let's take this impulse here. Let's call this, at t, at some t. This is U of t is approximately equal to a delta function at t times whatever that little infinitesimal area is there, which I'm going to claim is U of t times a little delta t. Okay, so whatever the let me just write this as this delta t. So the amount of delta function at this point that I need to capture that area is, okay, this little area here. It is the height U of t times the width delta t. That area needs to be in that delta function. This delta function has to have an area equal to that U of t, that height, times that delta t. Okay? And so here's where it gets kind of cool, is we can consider this infinitesimal series of teeny, we can take the limit as delta t goes to 0. So now this area is infinitesimal, and this is a continuous train of delta functions. I hope that makes sense. So we're going to take the limit as delta t goes to 0. This becomes an infinite train of infinitesimal delta functions, infinitesimal delta functions. Which is another way to say, at every instant in time, each of these U of t's at every point in time is acting like a little infinitesimal delta function. It's kicking my system this hard, and then a little harder, and a little harder, a little softer, a little softer, a little harder, and like these are each little infinitesimal delta functions with infinitesimal, as I take delta t goes to 0, these have infinitely small areas, but they add up over time because this is a continuous variable now. So that's what I'm going to draw here, is now the solution x of t is going to equal the sum of whatever my initial condition response is. So I always am going to have some, let's say, x naught, and at time 0, I'm going to have my initial condition response. Okay, so this is my initial condition. Let's say this is time 0. Okay, so I have my initial condition response, and then I'm going to have the effect of all of these infinite trains of delta functions. So plus whatever my control input u is, the delta function, there will be a little delta function here, which is at time 0. I'm trying hard to get this actually right for you. So the first one is at time 0, and that would be u0 delta t times this delta function. So this is u0 dt in the b direction. So u0 at times delta t is how much area is in that delta function. And so at time 0, I go that much in the b direction. It's like an initial condition, a teeny little jump in my initial condition equal to b times u of 0 delta t. Okay, and I'm going to draw it a little bigger than it actually is. But of course, it's infinitesimal. This will be an infinitesimal height because of this is a dt. Okay, so there's that at time 0. And then at time, whatever, the next little instant in time, I'm going to try to draw this discretely. Now at time, whatever, delta t, I have another little jump, which is, u at that time, t dt times b. That's going to be a little tiny infinitesimal impulse response. Plus, and then it's going to be shifted, plus dot, 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 dot. And so I'm going to get a bunch of these shifted trains of impulse responses where each one of these impulse responses is going to have magnitude u at that instant in time times dt. That's going to be the area, of u of t. This is how much is in each of these little impulses that are continuous. Each of these little impulses is adding a little bit to my initial condition at time now, and the next dt, and the next dt, and the next dt, and the next dt. I get all these impulse responses. And if I add all of those up, and let's see how good I am, if my art classes have paid off. I've never taken any art classes ever. What I get is something that, at time 0, of course, I start off at x naught. And now all of these are adding up continuously to give me something, that's going to, so this is going to be decaying, but I'm adding an impulse in u, and so I keep adding these things that are then decaying, and I'll get some, response, and then whenever my control stops, eventually things will just decay to 0, okay, according to e to the at. So that's the picture, is that we have this sum of trains of impulses because of this u of t, but now we're actually ready to write this mathematically. So essentially this is, and I haven't actually done this before, I'm a little worried, or I haven't done this in a while, that I'm going to get something like x of t equals, and each of these things is an e to the a. Let's say that this is based at not delta t, but this is at some time tau. Okay, this is some time tau. So this is going to be this is starting at time tau, so it's e to the a t minus tau times whatever that little initial condition bump was, which is b u at that tau d tau. Okay, so at that little tau, at every little single tau, I have an impulse response with area u at that tau, whatever u was at that tau, that's the times delta t is the area of that impulse. So it jumps me to a place b u tau d tau. And then for all future times, the system decays according to the dynamics e to the at, but again centered at t equals tau. So e to the at minus tau b u of tau d tau. And I'm adding up all of these. I'm integrating from 0 to infinity over d tau. I'm adding up, when tau is 0, and tau is delta t, and tau is 2 delta t, and 3 delta t, this shifting average. So it equals my initial condition response, e to the at x naught, plus this integral from 0 to t, whatever time I want to measure this thing at some time x of t. This is integrating up until t. All of these little impulse responses, e to the a t minus tau times b times u of tau d tau. And so this is the area of my impulse response. This is the little, jump in initial conditions because of that impulse response. And this is the decay of that because of the dynamics. And I add all of those up, shifting in time. So this is the full answer. And this is a convolution integral. Convolution, this is a very convoluted argument, convolution integral. I think they're probably, if you slowed down or if you rewound or if you paused and convinced yourself, I think this does make sense, but this does feel a little convoluted. This was a long lecture, this convolution integral. And the way we say it is we would say, okay, let's define h of t equals e to the a t b. Then this integral here is literally defined as the convolution of h with u. That's like, this is literally the definition of the convolution of e to the at b with another function u of t. Convolution of h with u, where h, and again, h is called, I believe this is called the impulse response. This is the impulse response. Like literally, if I put in a delta function to u, this would be the response. And so what we have, now we can understand this kind of pretty simply. This response here is just the convolution, or the continuous shifting integral, or shifting sum of all of these teeny tiny little impulse responses, h, with the magnitude of u delta t. So whatever u is at this time times delta t, that's how much impulse response I get. And then at the next instance, whatever u is at that instant times delta t, that's how much impulse response I add there. And I keep adding these little teeny tiny little infinitesimal delta function impulse responses in this kind of time shifting way. And if I add all of those up, I get my true system response, x of t. Okay? So that was a lot, but I hope this was all, all the steps were simple and made sense, building on this delta function up until this full convolution integral. All right, thank you.